This article is about the operating system. VME may also refer to the Vme bus computer bus. VME is a mainframe operating system developed by the UK company International Computers Limited. Originally developed in the 1970s to drive Icl's then new 2900 series mainframes. The operating system is now known as OpenMA, incorporating a Unix subsystem, and runs on Icl Series 39 and Trimitra mainframe computers, as well as industry-standard x64 servers. Origins. The development program for the new range system started on the merger of International Computers and Tabulators and English Electric Computers in 1968. One of the fundamental decisions was that it would feature a new operating system. A number of different feasibility and design studies were carried out within Icl, the three most notable being Vme B, targeted at large processes such as the 2970, 2980ths, and developed in Kids Grove, Staffordshire, and West Gorton, Manchester. Vme K, targeted at the mid-range systems such as the 2960 and developed at Bracknell after the original design for these small processes. System D was dropped. Vme K was developed and introduced to the market but was eventually replaced by Vme B. Vme T, which was never actually launched, but warrants a mention as it was conceived to support fault tolerance, and predated the efforts of the successful American startup company Tandem Computers in this area. The chief architect of Vme B was Brian Warboys, who subsequently became Professor of Software Engineering at the University of Manchester. A number of influences can be seen in its design. For example, Multics and Icl's earlier George III operating system, however it was essentially designed from scratch. Comparisons. Vme was viewed as primarily competing with the System 360 IBM mainframe as a commercial operating system, and adopted the EBCDIC character encoding as a creation of the mid-1970s, with no constraints to be compatible with earlier operating systems. Vme is in many ways more modern in its architecture than today's Unix derivatives or Microsoft Windows. Nomenclature. When New Range was first launched in October 1974, its operating system was referred to as System B. By the time it was first delivered it had become Vme B. Vme K was developed independently, and was delivered later with the smaller mainframes such as the 2960. Following a financial crisis in 1980, new management was brought into Icl. An early decision of the new management was to drop Vme K. Thus, in July 1981, Vme 2900 was launched. Although presented to the customer base as a merger of Vme B and Vme K, it was in reality the Vme B base with a few selected features from Vme K grafted on. This provided the opportunity to drop some obsolescent features, which remained available to customers who needed them in the form of the BONVMe option. The 2900 suffix was dropped at system version 213 when Icl launched Series 39 in 1985 as the successor to the original 2900 series, and the open prefix was added after SV294. Vme became capable of hosting applications written originally for Unix through a Unix System V Release 3 based subsystem, called Vme X, adapted to run under Vme and using the ASCII character encoding. The most recent incarnations of Vme run as a hosted subsystem, called Supernova, within Microsoft Windows, or SUSE or Red Hat Enterprise Linux on x86-64 hardware. Architecture. Vme is structured as a set of layers, each layer having access to resources at different levels of abstraction. Virtual resources provided by one layer are constructed from the virtual resources offered by the layer below. Access to the resources of each layer is controlled through a set of access levels. In order for a process to use a resource at a particular access level, it must have an access key offering access to that level. The concept is similar to the rings of protection in Multics. The architecture allows 16 access levels, of which the outer 6 are reserved for user-level code. Orthogonally to the access levels, the operating system makes resources available to applications in the form of a virtual machine. A virtual machine can run multiple processes. In practice, a VME virtual machine is closer to the concept of a process on other operating systems, while a VME process is more like a thread. The allocation of resources to a virtual machine uses a stack model. When the stack is popped, all resources allocated at that stack level are released. Calls from an application to the operating system are therefore made by a call that retains the same process stack, but with a change in protection level. The resulting efficiency of system calls is one of the features that makes the architecture competitive. Communication between virtual machines is achieved by means of events and shared memory areas. The hardware architecture also provides semaphore instructions INCT and TDEC. Files and other persistent objects are recorded in a repository called the catalog. Unlike other operating systems, the file naming hierarchy is independent of the location of a file on a particular tape or disk volume. In days where there was more need for offline storage, this made it easy to keep track of files regardless of their location, and to move files between locations without renaming them. As well as files, the catalog keeps track of users and user groups, volumes, devices, network connections, and many other resources. Metadata for files can be held in an object called a file description. Interrupts are handled by creating a new stack frame on the stack for the relevant process, handling the interrupt using this new environment, and then popping the stack to return to the interrupted process. OMF compiled object code is maintained in a format called OMF. Unlike in many other operating systems, this is also the format used by the loader. Various compilers are available, as well as utilities, notably the collector, which links the code in several OMF modules into a single module, for more efficient loading at runtime, and the module amender, which allows patching of the instructions in an OMF module to fix bugs. Using assembly language syntax. SCL. The command language for VME is known as SCL. It can be likened to scripting languages such as JavaScript, though its surface syntax is derived from ALGOL 68. SCL is designed to allow both line-at-a-time interactive use from a console or from a command file, and creation of executable scripts or programs. The declaration of a procedure within SCL also acts as the definition of a simple form or template allowing the procedure to be invoked from an interactive terminal, with fields validated according to the data types of the underlying procedure parameters or using the default procedure parameter values. The built-in command vocabulary uses a consistent naming convention with an imperative verb followed by a noun. For example, delete_file or display_library_details. The command can be written in full, or in an abbreviated form that combines standard abbreviations for the verb and noun. For example, XF or DLBD. SCL is block-structured, with begin-end blocks serving the dual and complementary roles of defining the lexical scope of variable declarations, and defining the points at which resources acquired from the operating system should be released. Variables in the language can have a number of simple types such as strings, superstrings, booleans, and integers, and are also used to contain references to system resources such as files and network connections. It is possible to disassemble an SCL program from OMF back into SCL source code using the read_SCL command. However, the output is not always perfect, and will often include errors that would stop recompilation without user intervention. A simple code example can be seen on the 99 Bottles of Beer website. A more realistic example, where SCL is used to compile a program written in S3, is shown below. This example is taken from the Columbia University Archive of Implementations of Kermit. Begin whenever result GT0 plus underscore then plus underscore send underscore result underscore message find KMT underscore SRC KMT underscore OMF KMT underscore REL assign underscore library assign underscore library assign underscore library begin delete underscore file 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 end S3 underscore compile underscore defaults S3 underscore compile OMF equals asterisk KMT underscore OMF KMT underscore data underscore module S3 underscore compile OMF equals asterisk KMT underscore OMF KMT underscore DH underscore module S3 underscore compile OMF equals asterisk KMT underscore OMF KMT underscore A underscore module S3 underscore compile OMF equals asterisk KMT underscore OMF KMT underscore FH underscore module new underscore message underscore text underscore module OMF equals asterisk KMT underscore OMF KMT underscore help underscore MTM S3 underscore compile OMF equals asterisk KMT underscore OMF KMT underscore main underscore module S3 underscore compile OMF equals asterisk KMT underscore OMF KMT underscore PH underscore module S3 underscore compile OMF equals asterisk KMT underscore OMF KMT underscore PP underscore module S3 underscore compile OMF equals asterisk KMT underscore OMF KMT underscore SP underscore module new underscore message underscore text underscore module OMF equals asterisk KMT underscore OMF KMT underscore SP underscore MTM S3 underscore compile OMF equals asterisk KMT underscore OMF KMT underscore UI underscore module collect an asterisk KMT underscore OMF KMT underscore DH underscore module an asterisk KMT underscore OMF KMT underscore A underscore module an asterisk KMT underscore OMF KMT underscore FH underscore module an asterisk KMT underscore OMF KMT underscore help underscore MTM in asterisk KMT underscore OMF KMT underscore main underscore module an asterisk KMT underscore OMF KMT underscore PH underscore module an asterisk KMT underscore OMF KMT underscore PP underscore module an asterisk KMT underscore OMF KMT underscore SP underscore module an asterisk KMT underscore OMF KMT underscore SP underscore MTM an asterisk KMT underscore OMF KMT underscore UI underscore module NEWMODULE suppress retain LISTMODULE perform compile underscore SCL out equals asterisk KMT underscore REL Kermit cod equals NOTIFWARNINGS opt equals fill end commands illustrated in this fragment include whenever assign underscore library delete underscore file S3 underscore compile new underscore message underscore text underscore module and compile underscore SCL which compiles an SCL program into object code. The collect command combines different object code modules into a single module, and is driven by its own local command file, which is incorporated in line in the SCL between the delimiters, and ++++. The subcommands input and Nodal identify the names of the input and output modules, suppress and retain determine the external visibility of named procedures within the collected module, and listmodule request a report describing the output module. Note that is used to separate the parts of a hierarchic file name. A leading asterisk denotes a local name for a library found using the assign_library command. The number in parentheses after a file name is a version number. The operating system associates a version number with every file, and requests for a file get the latest version unless specified otherwise. Creating a new file will by default create the next version and leave the previous version intact. This program, however, is deliberately choosing to create version 101 to identify a public release. Enhanced security variants as a result of ICL's heavy involvement with delivery of computer services to the UK public sector, in particular those with special security requirements such as OPCONCCIS. It was an early entrant into the market for secure systems. Vme formed a core of ICL's activities in the secure systems arena. It had the advantage that as the last large-scale operating system ever designed, and one built from scratch, its underlying architecture encompassed many of the primitives needed to develop a secure system, in particular the hardware-assisted access control registers to limit to privileges that could be taken by any process. This led to the UK government's Central Computing and Telecommunications Agency funding Project Spaceman in the mid-1980s for ICL Defence Technology Centre to develop an enhanced security variant of Vme. ICL launched this as a pair of complementary products, with the commercial release being called High Security Option, and the public sector release, including government-furnished encryption technologies, being called Government Security Option. HSO and GSO were formally tested under the CESG UK evaluation scheme, one of the predecessors to ITSEC in Common Criteria, and in doing so became the first mainstream operating system to be formally certified. Series 39. The Series 39 range introduced Nodal Architecture, a novel implementation of distributed shared memory that can be seen as a hybrid of a multiprocessor system and a cluster design. Each machine consists of a number of nodes, and each node contains its own order code processor and main memory. Virtual machines are typically located on one node, but have the capability to run on any node and to be relocated from one node to another. Disks and other peripherals are shared between nodes. Nodes are connected using a high-speed optical bus, which is used to provide applications with a virtual shared memory. Memory segments that are marked as shared are replicated to each node, with updates being broadcast over the internode network. Processes which use unshared memory segments run in complete isolation from other nodes and processes. Development process. Vme was originally written almost entirely in S3, a specially designed system programming language based on Algol 68R. Although a high-level language is used, the operating system is not designed to be independent of the underlying hardware architecture. On the contrary, the software and hardware architecture are closely integrated. From the early 1990s onwards, some entirely new Vme subsystems were written partly or wholly in the C programming language. From its earliest days, Vme was developed with the aid of a software engineering repository known as CADES, built for the purpose using an underlying IDMS database. CADES is not merely a version control system for code modules. It manages all aspects of the software lifecycle from requirements capture through to field maintenance. Multiple versions of each of these components could exist. The algorithms were written in system development language, which was then converted to S3 source by a preprocessor. Multiple versions of the same modules could be generated.